Welcome everybody. We are going today to finish the part on index construction. So as you can see on the image, this is because we are building great things. We are trying to index absolutely huge collections that either do not fit in the memory of your computer, but even would not even fit on a single hard drive, right? So we'll see that there are even techniques borrowed from big data for this. If time permits, we'll also start the next series, which is about index compression, because it's nice, of course, to be able to do things on a large-scale cluster in a data center, but this costs a lot of money. So we can also compress things and try to look at the amount of storage that we need, and it turns out that we can squeeze a lot of things into less space. However, before we start, I have a few questions that I'd like to ask you in order to check your knowledge of the previous week, and we'll see how you do, and then I'll move on with the construction of indices. So here you go. So this is the first question I have for you. Let me start it. So the question is, how many terms or types? So these are the what you have in a standard inverted index. Can a 4-7 B+3 of height 3 contain at least? Last time it was at most, right? But this time it's at least. Is it 27? Is it 48? Is it 64? Or is it 96? Oh, what am I doing? I think it's just a shortcut that wasn't activated correctly. All right, so these are the answers. So is the majority correct? I'm not sure. So the majority says 48. All right. It turns out that the correct answer is 96. So can anybody explain among the two of you who did 96, how did you compute 96? Anybody?
6 times 4 times 4.
Yes, exactly. And the 6 is actually 2 times 3, right? So let's look at top down, right? So let's start at the top of the tree. So at the top of the tree, we have 2 children, right? So maybe those who picked 48 thought, okay, we start with 1 because the root can have only 1 key. But if the root has only 1 key, then it has 2 children, right? So if there are 2 children, then we have two hierarchies at the top level. Then 4 is the minimum for the next one, then 4 again. And then at the end, it's 3 keys on every leaves, right? Because 4 to 7 children means 3 to 6 keys for the non-root nodes. So it's 3 keys on every leaf. So you have 2 times 4 times 4 times 3. And if you compute that, you can do it in your heads. That's 96, all right? So congratulations to those of you who found 96, and I hope it's clear for those who said 48 that it's because if the root has only one child, then you can remove it. It's useless, right? So you only get a root if it has at least 2 children, but the minimum of 4, of course, does not apply to the root, and this is why 2 is the actual minimum for the roots. Okay, very good. Let's move on. Here's another question. What is the Sumbex representation of paper? So you might remember that this is for the sound footprint, right? It's in order to see how a word sounds for spell check. So can you try to compute this one? All right, so here we also have a majority about P160. Some of you said P116. Okay, so can somebody explain how you arrived to the correct answer of P160? Or should I do it? All right, let me do it. So P remains, right? So the first letter, you keep at it as the first letter, so it's P. Then A is a vowel, so it's a 0, so P0. Then the next P is a 1, so P01. Then we have an E, which is a vowel, so it's 0, so P010. And then R corresponds to 6, so it's P0106. All right. So the next step is what do? We eliminate duplicates. So that's nothing. I'm doing everything in my mind right now. So there is absolutely no duplicate here, right? Because we have P0106, and there is never 2 digits that follow each other and that are the same. So the next round of things is we remove the zeros. So now we are left with P16, right? And then we pad with zeros because we need 4. So at the end, we add the 0. And this is how we arrive to the answer P160. Why is the answer P116 incorrect? It's because the first one would have corresponded to the first P in the word, but the first P does not get replaced by anything. We just preserve it, but we do not encode it into a 1. So this is why there is only a single 1 corresponding to the third P, to the third letter of the word paper. All right. In the chat, exactly, we have somebody who gives an explanation as well. Perfect. If P to start with, and then skip vowels and add 0, exactly. And do not forget the duplicate elimination, even though in that case, we do not need it. Okay, so next question. What is the Jackart coefficient on the sets of 2 grams or bigrams associated with computer and computer? All right, 7 answers so far. Let me start looking into the answers. So now we have some who say the majority is for 7/9, right? 7/9. And 7/10 and 8/10 are the next two. Okay, so there is neither an agreement on the numerator nor an agreement on the denominator. All right, so let me solve it with you, but I'll still allow you to change your answer as we go, just to see the evolution. Now we have a majority as 0.7. All right, so what are the 2 grams? So we need a sliding window, but we also need $1 and $1, right? So for computer, we have $C, CO, OM, MP, and so on, all the way to ER and $R, right? And then the same for computer. So first, let's look at the K grams that they do not have in common. The ones unique to computer, well, it's obviously CO and OM, right? Then there is a bigram that is unique to computer, that is CM, right? So we have 3 bigrams that are in neither. Right? Then how many do they have in common? Well, there is $C that they both have in common. Then they have MP, PU, UT, TE, ER, and $R. So they have 7 in common. 7 gives us the numerator, right? So it's 7 over something, right? So yeah, I should see the answers with 8 disappear slowly, hopefully. So it's 7 over something. And how do we know the denominator? Well, it's 7 plus those that are not in the intersection, and we saw that there's 3 of them, right? So 2 of them, CO and OM, are on the side of computer, and CM on the side of computer. So 7 plus 3 gives us 10 in total for the union of all the bigrams, and this is how we get 7/10, which is the actual correct answer, right? All right. And the last one, and then I'll start with the lecture. How does the dynamic programming table, remember, look like for computing the edit distance or the Levenstein distance between a word and itself? Does it have zeros on the diagonal? Does it have zeros all over the board, all around the borders, top left, bottom right? Is it filled with zeros everywhere, or does it have consecutively decreasing integers on the diagonal, like 10, 9, 8, and so on? What do you think? Oh, there is a big majority here. Zeros on the diagonal. Why is that? Anybody?
So from the chat, we need 0 operations to change a word to itself.
Exactly. And on the diagonal, remember that you have every time the distance between a prefix of the word, like for example, the first 3 letters, and the prefix of the same word with also 3 letters, for example, right? So you're always comparing a prefix with itself all over the diagonal, and this is why you get 0. And here you don't need to do the dynamic programming for that. It's something obvious, right? The distance between one word and itself is always 0, and that applies to the whole diagonal. I leave it to you as an exercise to find counterexamples for the others in order to prove that the others are incorrect. Okay, so let me now move to the slides, and they should appear in just a few seconds. Wonderful, magic of the metaverse. All right, so now Where is? Give me just 1 second. I need to find my my stick. And here I am. I have it. You see. All right. So we are trying to build this thing here. That's a standard inverted index. Remember that it maps all of the terms after all the post-processing we did, the pre-processing, sorry, to here, the length of the associated postings list. And here we have the posting list, right? But this can be huge, right? We can have like a million terms, we can have billions of documents and so on. So how do we build that? Well, we saw that we have one, actually it's already a compression technique kind of to fit, because while we process this index as intermediate constructs, when we are in the middle of building it, we have these pairs of term document ID, right? But we saw that the terms can take some space. So we use a technique that happens to be called dictionary encoding by database people, that instead of repeating the terms every time, we encode the terms with IDs. And that can be, for example, 1, 2, 3, we just enumerate them and they get a number, just like the document IDs, right? In that case, I just wrote T1, T2 in order to not confuse them with the document. This is basically just an ID for the term instead of the actual term. And of course, this assumes that you have a separate lookup table where you have the mapping between the ID of the term and the actual term, right? But what you gain here is that the terms are just stored once exactly in that term-to-term ID mapping, right? But in the actual pairs of term document, you have the term ID and the document ID. So now you have term ID, document ID pairs, right? Okay. Then we looked at the overall idea, right? Which is that we have all these documents that do not fit in memory. And what we do, we have this reflex coming from big data, we shard. So we cut into slices like this in such a way that each one of these slices is something that we can handle with our memory. So we let's say we have a machine with 16 gigabytes of working memory. Then I'm assuming here that this can be processed to build an index with 16 gigabytes of working memory. It doesn't have to be the actual size of this, right? Because it might be that this is only 10 gigabytes, but then there is some inflation when you actually have the intermediate values in memory that could grow the data to 16 gigabytes, right? But this is chosen, the size here, in such a way that you can process it with the memory, that there is enough, right? And so you shard and you shard and you shard, and then we'll process them one by one. So I already showed you a high-level animation last time, but now I'm redoing it, but zooming in with the first technique that is called BSBI. BSBI for blocked sort. It's almost a tongue twister, this thing, right? So blocked sort-based indexing. It's like she sells seashells on the beach. The shells she sells are seashells. Well, blocked sort-based indexing is what it's called. But BSBI is just so much easier to say. So I'll say BSBI. So in BSBI, this is what we do. We take one shard. So let's take the first one. So we take one shard. We are going to parse the documents in there, and we are going to read, after all the pre-processing, this term ID, document ID pairs into memory. So it's assuming we do this term-to-term ID mapping, right? So the term-to-term ID mapping is going to be somewhere. It's going to not take too much space, right? Usually this takes a bit of space, but not too much. So we keep it in a corner of our memory somewhere. And we just have the terms associated to the term IDs and in such a way that we can look them up efficiently. And once we have that, we just build in memory all of these term ID, doc ID pairs that are just created and created and created until it fills the memory, right? So this is why we pick the size in such a way that this occupies the entire memory. So now we have just term ID, document ID pairs, right, that we created out of this. So this is the set of word semantics, because now we don't care about the order, this is all lost. And we don't care about the number of occurrences, this is all lost as well. All right, so in order to create this huge lake, if you call it that way, this huge lake of term ID, document ID pairs, you have two strategies. The first strategy is to start by building the term ID term mapping. So this for the encoding of the terms for the entire collection once and for all. So you do a first pass, and then you build the term-to-term ID mapping, right? Or even if you do it just for the shard, you just do a first pass, right? And then you have this term-to-term ID mapping. Let's say for the entire collection, it's done. And then you do the once you have this mapping, you parse the document, and every time you have a term, you look it up here, you take the term ID and you put it in the you use the term ID in the memory. There is a second technique, which is to not do it in advance. So you don't prepare the term-to-term ID mapping statically at the very beginning. Instead, you just do it on the fly. So every time you see a term, you just look it up. Look it up in there. If you find it, great. Then you use the term ID that you've already assigned before. If you don't find it, then no problem. You just create a new term ID, and then you use it. So either a first pass of the entire collection, and then you create the mapping, and then it's done, or dynamically, on the fly, you create every time you see a term and a document ID, you look up an existing term ID or create one if it doesn't exist, and create the term ID document ID there. All right, so two strategies for the term IDs. All right, so now we have this. We have this term-to-term ID mapping. We have this enormous lake filling the entire memory of term ID document IDs pairs. So what do we do next? Anybody? What do I do with this? Words, 4 letters, starting with S. Yes, I see on the Zoom chat.
Sort.
Yes, exactly. We sort. We sort by term ID, right? So indeed, we sort all of that. So now I have nicely sorted everything. It's like this artist. I don't know if you. I think it's Ursus Verli, or so he's tidying up the like art and paintings and so on. So we are just playing basically Ursus Verli here, and tidying up everything by grouping the term ID document IDs together like this. So all nicely sorted by term ID, but not only term ID. If it's the same term ID, we also sort by document ID, right? So we also have them in the order of the document ID. All right, so now I have my term ID document ID pairs, but all nicely sorted, and I write it all back to this. So I'm done with my batch, and then I just continue with the next batch and the next batch and the next batch, and every time I just read up into memory, sort, and write back to disk my term ID document ID pairs. And once I'm done, I basically have on disk as many lists of term ID document IDs as there were batches. Maybe I have 100 of them, right? Let's assume I have 3 for the purpose of illustration of what happens next. Do we have a question in the chat?
I don't think so.
Oh, it was sort. Yeah, I see. It was the answer to the previous question. I just see this little red number whenever there is a pending chat message. All right, but don't hesitate to ask questions, right? You can ask questions at any time. All right, so now I'm assuming we did it 3 times. There were 3 shards, and 3 times we created these term ID document IDs, sorted them, and wrote them back to this. So let's say this is the first batch, this is from the second batch, and this is the third batch. In the last phase, this is the merging phase, I'm going to merge all of this because, of course, now I need a standard inverted index, just one, right? I still have my term ID to document ID, sorry, my term to term ID mapping right there. So I'm going to just put pointers here, here, and here. It's actually an algorithm quite similar to the intersection and union of posting lists, right? Where you have a pointer on every one of the inputs, and then you move them jointly through the data. So we start here, we start here, we start here. And then we start, let's say yellow is the smallest one. So we just start here building the standard inverted index, starting with the yellow term. So of course the yellows are, because it's all sorted, right? So they all start with yellow. And here there is no yellow, but this is because there's no yellow at all, right? So we know that for sure we can just ignore that for the yellow term ID, right? So then we just traverse that exactly like the union. This is actually literally the union algorithm for a single term, right? So it's the union algorithm that we just traverse this until we are done. So here, no more. You see it switched to the red, and there's still one here. And now I'm done. Now I can move on to the red, 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 red. Now I'm going to do it jointly on 3 of them. Red is the next one. So of course, every time I have the term IDs here, right? But I look up the term and then I use the term in there and I build my standard inverted index. All right. So now I have the, all right. So this is the union algorithm again, right? All right. And now the green, and then I fast forward, right? So you understood the principle, right? We just jointly traverse everything in parallel, and we build the standard inverted index, right? And then maybe at the end, if the order of the term IDs and terms doesn't match, you just sort all of that by term ID, but you can arrange, if you did a first pass with the term and term IDs, you can arrange that the order is exactly the same. So then you have it all sorted as well. All right, so what's the complexity of doing that? Well, the first step involves sorting, right? So it's going to be O of T log T. What is T? T is the total number of tokens. It's the total number of term ID, document ID pairs. So you know, you're computer scientists, so by now, probably you've heard at least 1,000 times in your lectures that the best algorithms for sorting are in complexity n log n, right? You also know that you shouldn't use bubble sort, hopefully by now. And as a consequence, the first step is T log T because we sort everything. And then the second step is going to be O of T because this is linear, right? It's like a merge sort if you want. So the last phase is going to be just linear. Of course, here I skipped a little bit so you can do the reasoning offline, but I directly took T log T. In fact, you would have to consider that it's every time the size of the batch, right? So it's T, if you call the size of the batch, I don't know U, then it's U log U, right? For each batch, and then you'd have to renormalize and multiply by the number of batches. But if you take that overall, then that gives you T log T here and T in there. And as a whole, the two together give you T log T. That shouldn't surprise you very much, right? Because if you did it on a single pass on a single machine, that's kind of O log T, and that basically shows you that it's the sorting that is the actual bottleneck in there. All right, so the complexity is T log T, but in practice, it feels more like O of T. Why is that? It's precisely because the log in there, actually, you're only sorting batch by batch, right? You're not sorting the entire collection until you merge. So this is why the constant here isn't so much, this is the bigger constant, probably because of the disk access, right? That here you have to access the disk and this is all in memory. So in practice, that very much feels like O of T, because the constant in front of that one is a bit smaller. Right? But it's really just a feels like. It's like the temperature outside, right? It can be 10 degrees, feels like 5. So here it's O T log T, but feels like O of T in practice. All right. Okay. As you can imagine, there's a lot of things we can improve in there. There's a few inefficiencies, and of course, some people have suggested other approaches to improve on the first one. And the one I'm going to look into right now is the single pass in memory index. It's easier to pronounce than the other one, but nevertheless, we love to affectionously, I don't even know how to pronounce that word. So we like to call it SPIMI, S-P-I-M-I, single pass in memory. Affectionately is the word I was looking for. So we like to affectionately call it SPIMI, single pass in memory indexing. All right. So in BSBI, we saw that when we process a block, we have these term IDs all over the place. But in SPIMI, we actually skip that phase. We don't even bother to use the term IDs because we directly build a mini standard inverted index in memory just for that batch, right? So we just start as if that was the entire collection. We just go through the collection and then add the terms. We maintain the structure right there, right? We can just use some B plus tree or a binary search tree or whatever structure you want that maintains the order in there. So you know that from data structures and algorithm. And here we have the document IDs, which will come in increasing order, right? Because you're just sequentially going through the collection. So you just append. And then at some point, you have this mini standard inverted index just for that batch. And what do? You sort it by term. Again, either you do it at the end, sorting by term, or you already use a sorting structure in advance that every time you insert, it's going to keep it sorted, right? Either way, you'll have the n log n no matter what, right? So either you do it, you keep it sorted as you maintain it, or you sort it at the end. All right, these are little variations. Okay, but at the end, you basically have this sorted list of terms and the sorted list of documents that contain them. This is our mini standard inverted index, which we flush back to disk because now we are done with that batch and we are going to the next batch and do the same all over and all over and all over again. Note that here we no longer have this term-to-term ID mapping held in memory, which is actually kind of nice because that means that we have even more memory to do this, because then we don't have a corner of the memory that is used for this mapping. So we have even more memory at our disposal when we do that. Okay, so batch by batch, I create my mini standard inverted index and write it back to disk. So at the end, I will have maybe 1,000 mini standard inverted indices that are all very impatiently waiting to be merged together, right? And in the end, this is what happens. Actually, we merge them. So you probably have guessed that the algorithm is always that merge algorithm that we keep using in this lecture. So we initialize the pointers right there. So here it's on the disk, right? What's very important, this is not in memory, it's on the disk. We can also write back on the disk. So this is disk to disk. But since things are sequential, it's fine. We don't need to actually store everything in memory. This is already sorted. So we just do it sequentially. So we start yellow, yellow. So, you know, we can take all of the postings corresponding to yellow. We can sort them. If you want to really take it even one step further, you can even have mini pointers that are on each list and apply the union algorithm. Or you can go brute force because maybe the list isn't that big and you just put them all in memory, sort them, and then flush them in the order, right? So again, there's plenty of variations of the ways we can do that. But anyway, at the end, I have here my merged list of postings in increasing order for this term. All right. Then I go to the next term and I do the same and I sort them, and that's red. Then I have green, no, I have blue, and then I have green, and so on. So you see term by term, and here it's already nicely sorted, right? So I just merge everything. And at the end, I have my very big standard inverted index that might actually be bigger than memory. But thanks to this merge algorithm that is linear and sequential, I can do it disk to disk, right? All I have in memory is when I build my list of the postings, right? And actually, if you think a bit more, if you have increasing document IDs in every batch, this is actually just the concatenation of the document IDs every time, right? So you see, you can even go more fine grained in there. You might also want to consider that if you have a B+3, 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 you might also incorporate in there the merging of the B+3s as well, right? So there's a few details that I'm skipping there, but this is in essence the idea, right? Okay, so this is it. So how does it feel? Well, in my first step, it was O of T log M. Why log M? Because what do I sort in there? I sort the terms, and M is what the name that I give to the number of terms. So N is the number of documents, M is the number of terms, and T is the number of tokens, right? And I'm sticking to this convention that the book also uses. So what we keep sorted in there in memory while we build the standard inverted index is just the terms. So it's M log M, right? M log M for sorting the terms. Here, this is just increasing. There is nothing to sort there. So this is why we have T log M. So M log M, but it becomes T when you actually do it sequentially, which is linear, right? So, all right, so it's within O of T log M. You can actually consider it as T times M log M, right? Divided by the number of batches. All right, but when you do the cooking and simplifying and so on, then you obtain that it's O of T log M. The second step is still O of T, right? This is just a merge. It's sequential, right? So there is no longer a sort in there. It's just linear. And then at the end, you end up into something that pretty much feels like O of T. Why do we also say that? It's because M is really very small. M is already the number of terms, which is much smaller than T. And you even take the log of that. So when you take the log of something that is very small, you almost get a constant, right? If you want to abuse it. All right, so we have O of T. Okay. BSBI, and SPIMI. These are the two first approaches. These approaches are designed for a single computer. We did it all with your laptop, basically, maybe using your entire disk with the 20 terabytes that you have, but using only 16 gigabytes of memory. But there are cases in which the size of your data will not fit on your disk. Maybe you have a petabyte of data to index, right? Maybe you're, I don't know, the British Museum or the Library of Congress in the US, so it doesn't fit on a single laptop, as you can imagine. But then there is a lot of technologies to store it on multiple machines that we will cover in the master's level in the big data lecture. But nevertheless, I want to give you a feeling of how the processing is adapted in order to work in the cloud like that, because it's actually very interesting. And that will give you a glimpse into a technology called the MapReduce that you might have heard of. Maybe you heard it in other lectures, like sometimes in machine learning, it's also used as a tool. But I will give you also a 101 of that, and then we'll see how we manage to build a standard inverted index on a huge collection in a cluster of machines. So what's the idea when we process data at that scale? Well, data comes in chunk. Well, that's not new, right? We already sharded the data on a single machine, right? Chunk is just a synonym for shard. We love these words like shard, chunk, block, and so on. It's just basically that we cut the data into slices. All right. So what happens is that we have all of these shards in there, and then we have this big query, and then we have the output. But actually, in the case of MapReduce, that is this framework invented by Google, back then, Google MapReduce, it's a very, very simple framework that basically applies a phase in parallel of mapping stuff. So you have a mapping function that maps the input data to some intermediate data, all in parallel, maybe on 1,000 machines. Then you have this spaghetti in the middle because you shuffle around the data across the cluster in order to put together what belongs together. Then you have a second phase in parallel with another mapping function that is called, this time it's called reducing. And then finally, you have the output data. This is a very simple framework, very generic, and it's amazingly powerful. You can index the web with that. And actually, this is pretty much what we are doing now. You can also consider that we are going to index the web. All right. So the way it works is that you have this mapping function that maps the input to intermediate output. Then you sort everything and shuffle around. That basically corresponds to sorting and partitioning. And then you map again. Okay. But this is very high level, and probably you didn't really visualize yet what's going on. So I have a great way actually to make you visualize. Let's hunt for Pokemons. So imagine that I went for a hunt of Pokemons last weekend, and now I want to count them. So I have all my Pokemons that are over there, and we need to count them. So maybe I have 500 of them, or maybe 500 million if you want, and they are all there, but there's only 10 different kinds of them, or maybe 100, or I don't know. Okay, so what I want in the end is for every Pokemon, I want to know how many I have of each one of these Pokemon. And I'm going to use MapReduce with that. So how does it work? Well, the idea is that we have mappers. This is something we actually do live in the big data lecture, right? So maybe you'll see it next year. So we have one person that is responsible for a chunk or a shard of all the Pokemons that they get. And this person is going to count within that shard here and produce intermediate results. So these are the counts, but partial, just for that shard. For example, there was one of this, one. I just know this one is Pikachu, right? I'm not sure about the names of the others. So here we have 2 Pikachus, right? And then there are the other Pokemons in these quantities. So this is the mapping phase that is local to just this shard of the Pokemons that we have. And what happens next is that we have reducers. These are other people that are going to be responsible for maybe 1 Pokemon or 2 Pokemon. So here, this person is responsible for Pikachu. So that means that she's going to receive all of these Pikachu pairs. Here, there was 1 here, 2 here, and so on. So these are from all the mappers. And so she receives these pairs in there. And of course, what she's going to do is sum them, right? Because we are counting. So 1 + 2 + 1 + 3 + 1 gives us 8. So this is the reduce phase. And when all of these people who are responsible for reducing are done, they will each produce one of these outputs. And there we are done. So we basically counted the Pokemons in parallel with the help of several people who did the mapping and several people who did the reducing. All right. So basically now you understand MapReduce. for counting Pokemons. But now we are going to do something else than counting Pokemons. We are going to actually build the standard inverted index for our collection. I have 4 more minutes to the break in order to start explaining that. All right, so we have our entire collection. Doesn't fit in memory, but now it doesn't even fit on disk, right? So it fits on a cluster of machines. Maybe I have 1,000 machines, but it's all sharded, right? So it's cut into shards. And I want to build this huge standard inverted index that probably is not even going to fit on a single machine, or even less in memory. So we shard the collection. That's something typically done in advance, meaning that this is on one machine, this is on another machine, this is on another machine. Maybe we have, I don't know, 10,000 shards. So imagine, or another way of putting it, this is the entire internet that you downloaded to your cluster, and you just sharded the internet or the web in quantities that fit every time on a single machine. So what we do next, we have the same thing as the Pokemon counting, except that now we are not counting Pokemons, we are just gathering the term documents pairs. So we have these same mappers. So every mapper is responsible for one shard, takes that shard, produces the term document ID pairs, right? So this is all coming from this local shard on one machine. Of course, this is not going to be a person, right? It's going to be a computer program, right? But I'm keeping the analogy here. So we have for document 1, we produce maybe these term documents. So these are also called postings, right? And then for document 2, we produce this. In practice, maybe there's going to be 10,000 documents in there, right? But I just put 2 in there. All right, so we have these postings from document 1, these postings from document 2. So you recognize the same structure as for the Pokemons, right? Except that instead of having the Pokemon and the counts, now I have the term and I have the document ID, right? But the structure is the same, it's all pairs. So what happens next is that the reducers are going to be assigned with terms. So for example, this reducer right here, again, it's a computer program, not a real person, but this reducer is going to receive, to be assigned the term information. During the shuffling spaghetti-ish phase, the reducer receives all of the key values there that have this term and the document IDs. And then the reducer is taking them and producing one row of the standard inverted index, right? So now we have the term information with the actual row, the actual postings list with here the frequency, so the size of the list, and then the ordered list of document IDs, right? And all of that every time, the mapping and the reducing, it's every time done on a single machine, but in parallel across machines. All right. And then at the end, what I have is that every reducer will produce a row or several rows of my standard inverted index. So this is how we have downloaded the entire internet onto our petabyte or exabyte scale cluster. And we have mapped everything with, I don't know, 100,000 machines, shuffled it around, and then built line by line these posting lists also in parallel on our cluster, right? So the way it works, it's actually magic. There is an architecture for that we study in more detail in big data, but basically there is a centralized network of machines with here a primary worker in there, and then all the secondary nodes in there. And what we do is we bring the query to the data, right? So the internet is basically stored on all of these machines, and on every machine we do this mapping on the same machine as where the shard is stored, all in parallel. Then we shuffle around, and then again we process the posting lists where they are, right? All right. And the magic of that is that the way it's stored on the cluster in blocks like that, or blocks, shard, splits. I warn you that there's plenty of words, right? Chunk, shard, block, split. This is all the same for the purpose of this lecture. So it's nicely, the internet is nicely sharded into these blocks, and every block corresponds to one mapper every time to process it. I'm done. This is MapReduce. Hopefully you enjoyed the Pokemon hunt as well, and that will give you a good analogy for the next time that you go more in depth into MapReduce. We are now at the time of the break. It's 3 p.m. So thank you very much for following, and I'm going to see you again in 15 minutes from now, where we look into online index construction, meaning if the collection moves. See you in 15 minutes. Thank you.